Folks, welcome to the next episode of Electromagnetism. Today we're starting something very special, the Laplacian. Let's get into it. Alright folks, welcome to the next episode of Electromagnetism. I'm very excited today to introduce you to the concept of the Laplacian. But before we get into it, let's get into the lecture. In today's lecture, we're going to be going back to the roots of electromagnetism. What is the whole point of electrostatics? The point is very simple, but it's one you should always keep first and foremost in your mind. The goal of electrostatics has always been to determine the electric fields. For an arbitrary charge distribution. This has been our goal from the beginning. Right? And we found many tools to help us achieve this goal. One of the most basic tools that we started with was the electric fields for a point charge, right? Coulomb's law. So let's write down all the tools we've accumulated so far to help us figure out the electric field for an arbitrary charge distribution. First, we had Coulomb's law. We just said that the electric field was a vector and it was an inverse square law, just like the gravitational fields. So Coulomb's law for a point charge said that the electric field due to a point charge is equal to 1 over 4 pi epsilon naught, that's my k, the amount of charge I'm considering, over r squared times the r vector. Actually, if I use the r vector, I have to put r cubed in the denominator. So let's use r hat. So this is Coulomb's law, the first thing we encountered, and it works pretty well for the most part if you have a simple charge distribution. But that's its pitfall, right? It only works for simple charge distributions. So let's write down its disadvantage. Only works for... Now, of course, it doesn't mean you can only use it for point charges. You can apply Coulomb's law for continuous charge distributions, but they better be pretty simple. Now, here's where our second tool comes in. If you have more of a symmetrical situation, such as an infinite cylinder or an infinite plane or something like that, then you can use Gauss's law, right? Gauss's law. If there's any English teachers in the audience, I advise you to stop the video immediately because I'll be making many grammar mistakes intentionally from here on. Gauss's law tells us that the dot product of the electric fields with the unit normal area vector is equal to the charge enclosed over epsilon naught. What the hell does that mean? That means that if we have some kind of a charge distribution, if we have some kind of a symmetric charge distribution, for instance this infinite cylinder, which extends all along the z-axis, then we can construct what's known as a Gaussian surface around the cylinder, so that the electric field protruding out of this infinite cylinder is parallel to the unit normal area vector of this Gaussian surface. And so since this dot product involves two vectors that are parallel, you can just multiply them. You can multiply the electric field's magnitude with the surface area of your Gaussian surface. And from there on, you can figure out the charge enclosed. And if you know the charge enclosed and you know the surface area of your Gaussian surface, you can easily find the electric field. So that's the whole point of Gauss's law. It's a very nice tool for helping us figure out the electric field, but it only works for symmetrical charge distributions. So that's the pitfall for Gauss's law. Let's write that down. Gauss's law only works for symmetrical charge distributions. And what are the symmetries we know? We know a sphere, we know a cylinder, and we know a plane. That's pretty much it. Charge distributions. Is there any other tools that we've gathered along the way to help us find the electric fields? Why, yes. When the work gets tough, you call in the electric potential. That's where the following comes in. The electric potential exists for one reason and one reason only. It exists because the curl of the electric field is 0, hence admitting a scalar potential function, which is the electric potential. whose negative gradient is the electric field. Now, the electric potential for a continuous charge distribution is as follows. It is 1 over 4 pi epsilon naught rho r prime, okay, d cubed r prime over r minus r prime. So this is the electric potential for a continuous charge distribution, where, let me just kind of explain what's going on here. You have 1 over 4 pi epsilon naught q, which is rho times v, that's q over r. That's all this is saying. 1 over 4 pi epsilon naught q over r. That's it. That's it. This fancy thing down in the denominator is just saying that, okay, hey, my source charge is coming from here. Let's say that's r prime, and I want to determine the field here. Let's call that r. So this is the field point where I want to find the electric potential, and this is the source point, or the source charge, where the electric potential is emanating from, right? So I'm just subtracting r minus r prime, finding the magnitude. All that's telling me is the distance between these two, the distance between these two. So this is just r minus r prime magnitude. Okay, so that's the electric potential. But it has its own pitfall, doesn't it? Because what does it rest on? Rho, right? What if you don't know rho? Well, why wouldn't you know rho? Well, you wouldn't know rho for the case of a conductor, for example, when you don't know, for instance, how much charge is induced on a surface. So rho can be hard to come by for a conductor. So let's write that down. This is only helps if you know rho, the volume charge density. Okay. All right, so we've got 3 rules that can help us figure out the electric field. Of course, this is for determining the electric potential, but after we get the potential, we can simply get the electric field by taking the gradient of the potential, right? Now, we've got these 3 covered, that's fine, but there's one more tactic, one more trick we learned in the last video that can help us figure out the electric field. And it only works for highly specialized charge distributions, but it works nonetheless. So why complain? Image charges, right? We found that via the uniqueness theorem, we found an analog for the image charge distribution where you bring in a point charge or a collection of point charges, or even a continuous charge distribution such as a disk near the surface of a planar flat conductor. And to find the electric potential associated with that distribution, all you have to do is find an analogous problem that satisfies the same boundary conditions but has easier electric potential to find. And indeed, we found that in such a case, image charges lead the way. So for example, in the previous lecture, we saw that if you bring in a point charge Q near the surface of an infinite grounded planar conductor on the xy plane, the electric potential associated with this charge distribution is the exact same as the electric potential associated with this charge distribution. We have Q minus Q. So you negate the charge and you separate it by the same distance from the origin. So that is the whole concept of image charges, which we discussed in the previous lecture. And now, today, we're opening a whole new page in our book. This is an extremely powerful tool to deduce the potential from which we can easily get the electric field. But once you have the potential, then the electric field is a home run. And this new tactic, this new method, is called the Laplacian. And that's what we're going to be talking about today, the Laplacian. This is an extremely powerful mathematical technique, and if you can grasp it, then the world is your oyster. You can truly solve almost any electrical potential problem that falls into these bounds. So let's talk about what those bounds are. When you don't know rho, this is when the Laplacian can come in handy. The Laplacian is simply Poisson's equation, which states that the second partial derivative of v. I know this is not the partial derivative, but let's just keep math simple here. The second order derivative of the electric potential is minus the volume charge density over epsilon naught. Now, if the volume charge density in a region is 0, then, so if rho is 0, then we end up with Laplace's equation, which has this second order PDE equaling 0. Okay, and so we're going to solve this equation for V, and and we're going to come up with something, and you'll see how awesome it is. Now, we have solved Poisson's equation, and we ended up with the equation for the electric potential, but now we're going to solve Laplace's equation, assuming that the electric potential V is separable. So we'll check that out. In fact, what better time to check that out than right now? Let's take a look at an example problem. Do you remember when it was dark in September? Here is another view of problem 1. Okay, so here's the problem we have. Two infinite grounded metal plates lie parallel to the xz plane. So here's the xz plane. Z-axis is right here, not shown. One at y equals 0 and the other at y equals a. The left end, x equals 0, right here in purple, is closed off with an infinite strip insulated from the two plates and maintained at a potential of V0 of y. Find the electric potential in this slot. Okay, let's take stock. What do we have? We've got two infinite grounded metal plates. They're metal, so they're conductors, right? Okay, so let's see. Is there any charge in this slot? No. Let's write Poisson's equation. Poisson told us that nabla squared V is the volume charge density over epsilon naught. There is no volume charge density, hence this is equal to 0. Hence we have Laplace's equation. Well, let's expand this in terms of partial derivatives. If nabla squared V is equal to 0, then the second order partial derivatives of V with respect to x, y, and z all add up to 0, right? Okay, so far so good. Just doing some regular good old vector calculus. Okay, now we're going to use something called separation of variables. Okay, this is a very powerful technique. And separation of variables assumes, out of nowhere, but assumes that the electric potential may be a product, a separable product of two functions. One function that is just defined in terms of x, and another function that's just in terms of y. Okay? Why do we have any right to assume this? Well, turns out that this pops out a solution, which is not a good reason at all, but who knows, maybe a lot of people tried different methods and separability is what worked. So, all I'm saying is that the electric potential function, we're assuming that it can be broken down into a function of just x times just a function of just y. For example, 3x times y. This could be a valid potential function, for example. Okay? So now that we have this, now that we are assuming that the electric potential function is a function of x and y multiplied together, let's plug that into this and see what happens. Now, before I go on further, I want you to notice something. I didn't draw the z-axis for a reason here. And the reason is because this charge distribution is symmetrical around the z-axis. Say what? Well, pick any 2 points that are different just by their z-coordinates. Can you distinguish these 2 points? Well, you might say this one is more to the right than this one, but remember, these are infinite planes. They don't stop. I mean, I could have kept drawing this infinite plane in any direction I wanted to, but I just had to stop at some point because I'd get tired. So the fact of the matter is that this point is no more to the right than this point is. Hence, we are symmetrical around the z-axis. Hence, there's no need for the z-coordinate in this problem. Okay, good. Well, now all we have to do is plug in this potential into this gradient equation and see what pops out. So we'll have partial squared, so nabla squared x of x times y of y all over partial x squared. This is small x, this is capital X, plus partial squared capital X of x, capital Y of y, all over partial y squared, and this is equal to 0. Okay, well, y is a constant when differentiated with respect to x, and likewise for x when differentiated with respect to y. So let's pop those out. So we're going to pop out y over here. So we're going to have y of y. Well, you know what? You know that it's a function of y, so why bother writing it? So partial squared x over partial x squared plus x partial squared y over partial y squared is equal to 0. Now I'm just going to divide both sides by the potential itself. What is the potential? It is assumed to be a function of x times a function of y. So x times y, x times y. This is going to result in, well, y over x over y gives us 1 over x capital X, by the way, capital X is a function of x, or small case x, and so we're left with the following. Okay, well, so what, you say? So this, notice that this right here is just a function of x, and this term right here is just a function of y. So what? Well, so this, I tell you, if a function of just x and a function of just y sum to give us 0, what does that mean? Maybe it'll become clearer if I move the function of y to the other side. What's that going to give me? Let's see. Let's bring it back here. Hopefully you can still see anything right here. This is going to give us 1 over x partial squared x over partial lowercase x squared is equal to 1 over y partial, there should be a minus sign since we're moving it over, partial squared capital Y partial y lowercase y squared. Now this is a function of just x equal to a function of just y. How can that be unless they're both constants? Therein lies the big idea, the big breakthrough of separation of variables. Right, so these two guys had better be constants. And in fact, they're constants such that one constant is the negative of the other constant. Okay, well, let's take that idea and run with it. Let's run with it. So let's take this. This is obviously equal to a constant. Now that, well, not obviously, nothing is obvious here. If you have any questions, leave them down in the comments below. But now we know that this is equal to a constant. So just multiplying through by x on both sides, I'd have xc1, just looking at this left-hand side here. And then for the y term, I'd have, hopefully you can see down there, yes, partial squared capital Y over partial lowercase y squared is equal to what? Well, I could make it equal to minus yc2, but I will not. Instead, I will choose to use the same variable, c1, except make it negative, since I know the two constants are negative of each other. So minus c1. All right, so far so good, you say. Now, at this point, you might, your differential equations gear should start turning. You should say, wait a second, wait, stop, just stop. I differentiate something twice and I get the same thing back? Does that not sound like an exponential? And I differentiate something twice and I get the same thing back with a change of sign? Does that not sound like a sinusoidal? Indeed it does. Indeed it does. And so, from this, I deduce that x and y must either be exponentials or sinusoidals for this separation of variables technique to work. So, I can choose x or y to either be sinusoidals or exponentials. And I have to choose based on their physical behavior. So I'm going to explain that in a bit. So x can either be an exponential or a sinusoidal, and y could either be an exponential or a sinusoidal. Now you might say, hey, stop there, trying to play games with me, because x is the one with a positive sign, hence it must be that x is the exponential term, and y is the one with a negative sign after two derivatives, hence it must be the one with the sinusoidal. To which I say, you're right, but take a look. I could have easily made this the negative one and this the positive one, because all we require is that one constant is the negative of the other, and that the sum of these two terms is 0. I could have easily made this the negative one if I so chose to. And so you have to choose which derivative you make negative based on the physical conditions. So let's take a look at the physical conditions, shall we? What do we have here? Well, what we have are something called boundary conditions to consider. Let's write down our boundary conditions, and those will help us decide what we should choose for x and y. What kind of function, exponential or sine? So I will use red to denote my boundary conditions. What are boundary conditions? They're simply limitations on what the potential can be at the boundaries. You notice that did I say it here? Two infinitely grounded metal plates. So these two plates are grounded, right? So usually you will see the fact that something is grounded using this symbol, an arrow pointing down, because pointing down to the ground. That's how you know it's grounded. So these two metal plates are grounded, meaning the electric potential on their surface is 0. So one of the boundary conditions we have is that the electric potential at y equals 0 is 0. So V of x comma 0 is 0. But the electric potential on the other plate is also 0, since it's also grounded. And where's the other plate? It's at y equals a. So here is our other boundary condition. The potential at x comma a is also 0. What else? Well, the potential on this insulating plate, or whatever it is, infinite strip, this infinite strip is held at an electric potential of V naught of y. And that's the case when x is 0. So when x is 0, when y is free to be anything it wants, we're left with that constant, or maybe not constant, we're left with that potential V naught of y. And finally, one more last thing is that as you move away from this plate, this purple plate, your potential should head to 0. Why? Well, there's no charges to be had in this slot. As such, we expect that as x approaches infinity, in other words, as you move in this direction, the electric potential approaches 0. It goes down. Okay, so those are our boundary conditions, but how in the world is that going to help me figure out if x is a exponential or a sine, or if y is an exponential or a sine? Here's how. Notice that my electric potential for V of x0 starts at 0, and V of xa ends at 0. What does that mean? That means that here, when I'm on the bottom plate, my electric potential is 0, and it can be whatever it wants in the middle, but by the time I come to the top plate, electric potential got to return to 0. What kind of function starts and ends at the same value? Is it an exponential or a sine? A sinusoidal, of course, right? A sinusoidal is the only kind of function that can, well, not the only kind of function, but in this case, out of these two choices, an exponential surely cannot return to the same initial value. Only a sinusoidal can do that, right? So we are left to conclude that in this direction, the correct function to choose is a sinusoidal. Well, what is this direction? It's the y direction. Hence, y is a sinusoidal. Okay, good. So y must end up with a negative sign. So let me make that negative sign official by making it blue, or as I like to say, avatar. Now, what about the x direction? Well, as we move in the x direction, we expect the potential to head off to 0, right? There's no returning back to the original potential. We don't have another plate here that's V naught of y. So the x function must be an exponential. X exponential, y sinusoidal. So now that we've figured out what functions we should have in the x and y directions, we can now write our potential function, or at least get started with it. All right, let's get into it. So we just figured out that x should be an exponential and y should be a sinusoidal. Let's write down a general linear combination of exponentials, which I shall write as a and b, okay? And a general combination of sinusoidals, c and d. Okay, whoa, what the hell am I doing? Why did I write a, b, c, d? Am I trying to recite the alphabet? No. What I'm trying to do is write a linear combination of exponentials. In other words, a basis function that can allow me to express all possible exponentials from two Starter exponentials, if you know linear algebra. So I'm going to have a e to the kx, b e to the minus kx. These two exponentials, if I mix and match them in just the right way, I can create any exponential I want in the world. Okay. And likewise for y, I'm going to create a linear combination of sinusoidals. C sine kx, d cosine kx. And this is the basis function that can help you create a general function just from sine and cosine for your series. So now that we've got a general equation for our x and y directions, let's impose the boundary conditions and cut out some crap from here. So let me show you what I mean. Let's start off with the first boundary condition. It tells us that the potential right here at the bottom plate has got to be 0. Wait, the potential at the bottom plate has got to be 0. You know what that means. That means we've got to plug it in and see what happens. This y is a function of lowercase y. And I have made a grievous mistake in writing x instead of y here. So pardon that, and we will be good to go. So this should be y right here. And x is a function of lowercase x. Well, all right. We know that when y is 0, the electric potential should be 0. So let's plug it in here. Okay, so y of 0 should be 0, is it? Let's see. So c sine of k times 0 plus d cosine k times 0. Okay, well, k times 0 is just 0. So let me just write 0 for here in the inside. Okay, well, sine of 0 is 0, no problem. So this whole thing goes away. But now we're left with cosine of 0, that's 1. So this tells us that d is 0. Heck, we just figured out one of the constants. This guy is 0. Voila. This guy is 0, so that the potential can be 0 at the lower plate. Okay, good. So this is 0 by the first boundary condition. Okay, see, that's why these boundary conditions are so powerful, because they help us cut out the crap, like d. We don't need d, right? In fact, it's gonna prevent us from achieving our desired potential at the lower metal plate. Let's impose the second boundary condition, shall we? So we have imposed the first boundary condition, so thank you. The second boundary condition states that the electric potential at this plate is held constant at V0 of y, although the potential itself might not be constant. Now this boundary condition is going to be a bit harder to implement, but we will implement it at the very end. So let's save the best for last. The third boundary condition says that as x approaches infinity, the electric potential should approach 0. Well, let's take a look at x. As x approaches infinity, this term is going to become smaller and smaller because it has a negative decaying exponential. But this term is going to fight. This term is going to be an anarchist, a rebel, a teenager. This e to the kx is going to grow and grow in droves. And we cannot let that happen. Because if this, as x approaches infinity, this term is going to get pretty damn big. And it's going to try to dominate. And so, the third boundary condition dictates that we make this 0. That the constant a be 0. So that this term doesn't exist. So this is true by the third boundary condition. Okay, so we are doing quite some work by imposing these boundary conditions. Let's take a look at that last boundary condition, number 4. So the boundary condition number 4 tells us this. The electric potential at A, well, where is A? It's right here, is 0. So at the upper metal plate, the electric potential is 0. Okay, well, let's plug it in and see what that dictates. So when y is A, the potential is 0. So let's plug that in. So y of A, now we are just left with this term. Remember that d was 0 by the first boundary condition. So c sine of k times A has got to be 0. Okay, that's what we're imposing. Now, well, c sine of k times A is 0. Well, let me just divide by c through both sides. So I'm left with sine of ka is 0. But wait, if sine of ka is 0, then what does Ka have to be? Ka has to be some multiple of pi. So that sine of that multiple of pi can be 0, right? Because remember, 1 is sine 0 whenever you reach a multiple of pi. That means Ka must be some multiple of pi, and hence K is n pi over a. Well, voila. Okay, not too bad. Not too shabby. So now we have completely reformed our original functions, our original guesses. Now my x function is b, e, and I'm left only with the decaying exponential, so that the potential may reduce to 0 as I head off towards the sunset, towards infinity. So be minus k to the x. Well, I know what k is now, so why don't I just plug it in? N pi times x over a. Voila. And how about y? So y is c sine ky, but I know what k is, simply n pi. And voila. But guess what? We have a lot of freedom. We have a lot of freedom because our potential v of lowercase x and y may be any linear combination of this x times y function, right? Because that's what we assumed in the beginning, that the electric potential v was a function of x times a function of y. Well, that's what we're saying here. The electric potential v is going to be some linear combination of this function of x, e to the minus n pi x over a, times this function of y, sine of n pi y over a. And by the way, if you're wondering, wait, where did my b go? Where did my c go? They were absorbed into this all expressing c sub n, expansion coefficient. That's the formal term. And so now we're left with this. We have this kind of massive but very nice potential function. C sub n, e to the blah blah blah, sine of blah blah blah. Okay, good. But there's one more step we can take. One last stab at this problem. And what is that? Well, we don't know what this expansion coefficient c sub n is. But there's a way we can figure it out. See, we've exhausted every single one of our 4 boundary conditions except one. There's one boundary condition which we have not exposed or exploited yet. And what is that? Well, it's the one we saved best for last, and that is the second boundary condition, which tells us that the electric potential at x equals 0 is held at v naught of y. Well, let's impose it. And we're going to use something very delicate, something you need to practice many times, and I say this from experience, to master it. And this trick is known as Fourier's trick. And I'll show you what that does in just a hot second. Okay, so let's plug in this boundary condition. When x is 0, I had better get v naught of y. Okay, let's do it. So let's move over here. Hopefully you still see. V of 0 comma y is equal to v naught of y is equal to my summation, my linear combination of c sub n. Now x is now 0, right? X is now 0. We're right here. So I'm going to have e to the minus n pi 0 over a. Well, what is this? Well, all of this is just 0. E to the 0 is 1. E to the 0 is 1. And hence, I need not even write this term. And so I'm left with sine of n pi y over a. Okay. So this is what I'm left with. Well, now, you might be thinking, how can I extract this c sub n from this summation? Is there any way, any desperate way I can extract this c sub n? Well, enter Fourier. Fourier gives us a very nice trick. He says the following. If you multiply both sides of this equation, in fact, before I even do that, let me state the fact that Fourier's trick is built on. The following integral, sine of n pi x over a times sine of n prime pi x over a dx, as you integrate from 0 to a, is going to equal a over 2 if n equals n prime, and 0 if n does not equal n prime. So this is almost kind of like a Dirac delta function kind of thing. But anyway, this is the Fourier straight. And so what we're going to do is multiply. Here it was, the variable of integration was x. Here we're dealing with y, same idea. I'm going to multiply both sides of this equation by sine of n prime. This is a prime, this is not. Okay, so notice that. So sine of n prime pi y over a, and I'm going to integrate this from 0 to a, however long y is tending, dy. Okay, and I'm going to do, of course, this is an equation, I've got to do it to both sides. So I'm going to take this v naught y that I have here, and I'm going to multiply it by sine of, okay, so this is what I have right now. Well, I know that every term is going to die except those terms which have n equals n prime. Okay, well, if n equals n prime, then this whole mess of an integral is just a over 2. The upper limit of the integral over 2. So we're just going to have on the right hand side, hopefully you can still see, on the right hand side I'm going to have c n prime, because only those terms where n equals n prime will survive, c sub n prime times a over 2 is equal to this crap, v naught of y sine of n prime pi y all over a dy. And you, as you integrate from 0 to a, and you need not know what this integral is. In fact, we don't know what it is unless we know what v as a function of y is. If we're given that, then we can integrate through and find the final answer. But in this case, we don't have to. In this case, we can just leave it as the expansion coefficient c sub n prime is equal to 2 over a times this behemoth of an integral, which goes from 0 to a of v naught of y sine of n prime pi y over a dy. All right, folks, so this is your answer right here. This was your answer. But you not only have to express what the potential is, but also what your expansion coefficients are. And that's what this is. So this is our final answer for this problem. And tomorrow, I'm going to show you 3 problems in which we actually use Laplace's equation to solve and crush 3 electric potential problems. So thank you for watching this episode. We'll see you in the next one.